My name is Aditya Yadav and I am demonstrating the first assignment of case 116 and I am demonstrating the first task. So this is a signal generator and this is our setup of piezoelectric speaker. The signal is coming out of this wire and this is connected to this, and there is a parallel connection between the piezoelectric input and simultaneously we are taking an output in the oscilloscope through the channel 1, and the second channel output is taken from the speaker this way. And as we change the input of the signal generator to the speaker, then this kind of thing happens. Like you can see that at 200 frequency, the peak to peak voltage is 2.2 something. Yes, around 2, it's average 2. Then if we change the input of the speaker, it increases rapidly. Like as you can see that it's approx 3 point something, and if we go above this, then it drops to 1 volt. So we can conclude that the resonance frequency is between 200 Hz to 400 Hz. Thank you.
This is my even ES 116 assignment 1. I am Aditya Yadav. I am going to explain task 1. In this task 1, there is an input signal of a piezoelectric speaker and the output magnitude of its and phase difference of its corresponding signals. So the aim of this task is to find the resonance frequency and plotting corresponding magnitude and phase response graph. And after finding this all, we have to calculate the quality factor of each resonance frequency. So according to my CSV data, my first resonance frequency is 352, which is the magnitude. As you can see that the peak of the magnitude is 4562 millivolt. The magnitude is taken in millivolt and the frequency is in hertz and the phase difference is in degree. So as you can see that in this graph we have the peak at 332 and corresponding this is the phase difference of the resonance frequency. Now we have calculated the quality factor of the resonance frequency. The formula, as you can see, that resonance frequency divided by the bandwidth is a range of frequency where the corresponding to the resonance frequency, the magnitude of the left lower limit and right lower limit of the frequency is 1 by 2 root 2 times of the magnitude of resonance frequency. So we have calculated the resonance frequency of our first resonance frequency 332 is 9.2, and the second resonance frequency is 2600. The corresponding peak value of magnitude is 1965, and the quality factor is 4.18. The quality factor shows the quality of the signal, that how good is the signal and how we are good at analyzing it, how good we can analyze it. This is the corresponding graph of the phase difference of the frequencies, and I have total taken the 47 frequencies from starting from 100 and then going up to 4000 hertz. Thank you.
Aditya Rateria. This is our second task of our assignment. And here, this is the function generator from which we have taken the signal wave for the sine input. And here is our LED and 330 ohm resistor. As shown here, we have taken 5 volt peak to peak and 5 volt DC offset. And here, the resistor is grounded. Now we are measuring the voltage across the resistor, which is connected to the channel 1 of the oscilloscope. We have connected the photodiode in reverse bias with the 5 volt and the Arduino. Now we'll measure the voltage across the 10 kilo ohm resistor which is connected from channel 2 of the oscilloscope. Hi, my name is Aditya Sathed. I will explain experiment 2, which is about the frequency response of photodiodes. The aim of our experiment is to analyze the behavior of photodiode across different frequencies and determine its characteristics. I showed the setup in the previous video, which consisted of the LED, photodiode, signal generator, two resistors, and an oscilloscope to measure the input and output signals. The procedure for our experiment was like the LED and the photodiode were positioned facing each other to maximize light transmission. It was shown in the video. We varied the frequency of the input signal while maintaining a constant modulation amplitude. At each frequency, we recorded the input and output voltages using the oscilloscope. We made two graphs. The first one is phase difference one, and other one is magnitude response one. So our first graph is gain versus frequency with minus 3 dB cutoff for the main peak. As shown here, we have two minus 3 dB frequencies, and the difference is the bandwidth of the photodiode. This represents the range of frequencies over which the photodiode operates effectively. Now this is our second graph. This graph shows multiple peaks. These are resonant frequencies of the photodiode. These frequencies are the frequencies at which the photodiode exhibits maximum of their sensitivity to light variations. The overall shape of the curve demonstrates how with frequency providing insights into its operational limitations and optimal conditions. The last graph is about phase difference. The phase between the input and output voltages varies as per the frequency varies in this graph. Now about the conclusion. The experiment provided valuable data on frequency response characteristics of the photodiode. We analyzed the resonant peaks, bandwidth, and frequency responses and gained a deeper understanding of the photodiode's behavior across different responses.